talking about was this result. So this is theorem. If E and L is algebraic over field K, and the minimal polynomial Fa, then the statement was that AA can be, the simple algebraic extension for A can be written as isomorphic to the polynomial Px divided by the ideal generated by Fa, and we have that Ka, the degree of Ka over K is equal to the degree of Fa. And in fact, 1A until A to the degree of Fa minus 1 is a basis of Ka as a K vector space. Okay, so we had done this, and I think one example of this was, for instance, C equal to R I, and then you can from this describe what the field is, for instance, the multiplication in this ring. Maybe I should have, right? Okay, so maybe I still write it out. So we have that, so the minimal polynomial I over R is x squared plus 1, and so therefore this has to be 2, so we see that 1 and I is a basis of C over R, and we can use this to describe the ring structure. If we have two elements, A plus BI times C plus BI, then we can just multiply this out formally. A C plus A D plus B C times I plus B D times I squared, and this is minus 1, so this is AC minus BD plus AD plus BC times I. So this defines us the structure of the field. Now so we have seen that a simple algebraic extension is finite. Now we want to conversely show that the finite field extension is algebraic. We have more precisely the following theorem. So let L over K be a field extension. So L over K is finite if and only if first L over K is algebraic, and in addition, and secondly, there exist finitely many elements A1 to say An in R, which then automatically have to be algebraic, such that R is equal to K A1 and An. Okay. So in particular, if you have a finite field extension, it is algebraic, so that means every element in R will be algebraic over K. And then in addition, we can add only finitely many elements. And conversely, and obviously also the converse. So now let's prove this. So we fix the degree, so let M be the degree of L over K. So then if I take any element A in L, we see that A, 1A is paired so on until A to the M are linearly dependent. Because L is an m-dimensional vector space over K, and we have m plus 1 elements. So thus there exist some elements P0 to Pm such that some I from 0 to n di a to the I, so this was m, is equal to 0. But this just means, and they should not be all 0. That means that they are linearly dependent. So obviously this is equivalent to the following. If I write f equal to sum I equal 0 to n di x to the I, then f of x is equal to 0, and this is a non-zero formula. So it follows that A is algebraic over K. So thus we have first seen that if L over K is finite, then L is algebraic. L over K is algebraic, which by definition means that every element of X is algebraic over K. Okay, now we have to see the second statement is clear, because e.g. for 2 if you see this is okay, just to show that if A1 to AN is the basis of R as K vector space, then obviously R is equal to K A1 to AN. Because if I add every element of a basis to it, I get already the vector space generated by K1 to AN is the whole thing, and so in particular like this I get. Okay, now I want to prove the other direction. So I make induction on, so what do I want to prove? I want to show that if I am in this situation, it's algebraic and there are finitely many elements, then it's finite. Well, so assume so the number of elements is n, so make induction of n. So assume L is equal, I make n1 larger, say, or I can just write, so we have L is equal to k a1 to an, which and I can put L prime C equal to k a1 to an minus 1. So then by induction the degree of L prime over k is finite, and in the end is algebraic over k, thus also algebraic over L prime, because k is contained in L prime. So if say L is equal to the degree of the minimal polynomial of an over L prime. So now this would be a simple algebraic extension. So then the degree of L prime of L over L prime, which is the same as L prime of an over L, is equal to this degree, and the degree of L over k is equal to the degree of L over L prime times the degree of L prime over k, which is L times the degree of L prime over k, which is finite. Okay, so this is a finite field. We just, this kind of trivial thing, you have find many elements. Each time you add an element, the degree is finite because it's the degree of the minimal polynomial over the field we had before. Okay. Okay, so this was this thing. So I want to very briefly talk about possible infinite algebraic extensions. Let me just that if you have any field extension set of all elements in the bigger field which are algebraic over the smaller field form also a subfield. So we want to see that, so let me just state it corollary. So let M be the set of all A in L such, so let L over K be a field extension. Here I make no assumption on how big this field extension is. Could be even something like with complex numbers over Q, so something huge. And let M be the set of all A in L such that A is algebraic over K. So I take all algebraic elements from this bigger field, then M over K. So then M is a subfield of L, and obviously M over K is an algebraic field extension. So that's so obviously by definition every element in M is algebraic over K, so M over K is an algebraic field extension if it is a field extension. So now you have to see this is a field. So by definition K is contained in M. So now, so in particular, it is a subfield of L which contains K. If it's a field, now it shows a field. So if I take two elements, A and B are elements in M, then if I take the field extension KAB over K is a finite algebraic extension. And we have that, so every element in KAB is algebraic over K. So that means KAB is contained in M. And you know, this is a field, so with so as KAB is a field, we have that A plus B minus A times B, and A divided by B are all elements in KAB. So thus we see that M is a field. So all the group operations, so it's a subset of a field, so which is closed under all the operations of a field, so it's a subfield. Because M is a field. An example, I think I have it here. Yeah. So something, you know, in number theory or whatever, this plays a role. You could look at, so put so Q bar, we define this to be a set of all, say, elements in C, such that A is algebraic over Q. This is called field of algebraic numbers. So by definition, this is a, so then Q bar is a field, and Q bar over Q is an infinite algebraic extension. Of Q. So you, for instance, you can study all, you can have here constructed a field which contains all elements which satisfy some polynomial equations with coefficients in Q. So this is some big field, but much smaller than the complex numbers, because complex numbers are uncountable, and you can easily see that this one will be countable, but still it's very big. And so in number theory, well, maybe we'll work over Q and so on, and in the most extreme over the algebra closure. Okay, so this is this example. Now, we can also use this kind of argument to show that if we close it down, if one wants to take the composition of algebra extension, that's algebra. So, how does this go? So that means, assume that L over M and M over K are algebraic field extensions. Then it follows that the big extension of L over K is also algebraic field extension. Note that this is not by itself a triviality, because in theory you're supposed to take, if you take an element, an element in L, which is the zeroth of a polynomial with coefficients in M, then you're supposed to find, to make it the zero of a polynomial with coefficients in K. That might not be so obvious, but it's actually not all so difficult, because let's just see how it works. So let's take an element A in L. So you have to find a non-zero polynomial with coefficients in K, of which this is zero. So show A is algebraic over K. So we know A is algebraic over M, so we better use that. So A is algebraic over M, so it follows we can write there exists some polynomial, say G, which I can write as sum I equal 0, so what did I want, to N Bi x Bi, such that G of A is equal to 0. Now, so in the end, I will not try to explicitly find this. I just this polynomial of which A is 0. I just will argue by the degree by just saying I take the field generated by these coefficients, and then we can see that we get something of finite. Let's see how that works. So we put n to be the field generated by, so the field extension of k generated by these coefficients. So then, so these elements are all, so I should maybe say that the 0, the n obviously are elements of M. No? So in particular, we know that M is algebraic over K, so we see this n is a field extension generated by finitely many algebraic elements. So then n over k is generated by finitely many elements, many algebraic elements. So thus it follows that n, the degree of n over k, is finite. And we see that our element A, lies in an extension. So we have that, and A is algebraic over n, because this G is a polynomial with coefficients. Obviously, G is a non-zero polynomial which with coefficients in n, which gives 0 if I put A into it. So A is algebraic over n. So thus NA over n finite. So thus NA over k is equal to NA over n times n over k is finite. And it follows therefore that every element of NA is algebraic over k by using our theorem again. So thus A is algebraic over k. So we don't try to explicitly find this equation, it's just by seeing that it lies in a finite extension, we know it must be algebraic. And this is just because this extension is finite, because we only need finitely many elements from this from this field M to say what the polynomial is of which A is a 0. And so we only need to work with those, and that is a finite extension. Okay. Okay. So that, for instance, means just as a corollary, if you have any, just as an observation, assume you have an element A in C, which is algebraic over Q bar, so which satisfies a polynomial with coefficients which are algebraic over Q, then this element must lie in Q bar, because it is algebraic over Q bar, so therefore it's algebraic over Q. So there are no algebraic extensions of Q bar. Okay. Where was I? Okay. So now, we come to some slightly new topic, which is field homomorphisms. Or rather, their extensions. So, we want to study Galois theory, and Galois theory is studying field extension terms of certain groups, and these groups are groups of automorphisms of the field. So we will have that. So if say L over K is the field extension, we will want to study this extension in terms of what is called the Galois group of L over K, which is the set of all K automorphisms of L. Remember, these are, so that is the set of all phi from L to L, isomorphisms such that phi restricted to K is the identity. So we will want to do this later, we're not yet there, but you can, so somehow we will very much study these automorphisms of fields, and in particular, or more generally, isomorphisms of one field to another. And so one question, one thing that we will need to do is to be able to extend an isomorphism from a smaller field to a bigger field in the field extension. And so in some circumstances there's a unique way to do this, in some circumstances there is at least a way to do it. And so we want to, so for this it is important to study extensions of field isomorphisms. I will in a moment. I already said more or less in words what I mean by this. Now I write a precise statement and you anyway see it. So basically the idea is you have an isomorphism, say from K to K prime, an isomorphism of fields, and you have a field extension L over K, and then you want to find an isomorphism between these bigger fields. So maybe I write it. So this was L prime. We want to find, so this is the aim, or study how many there are, such an isomorphism here. Okay, so let me state it first. So first I can give a proper definition. So definition. Let L over K and L prime over K prime be field extensions. Okay, let phi from k to k prime be field isomorphism. So isomorphism of rings, where these rings happen to be fields. So homomorphism of an isomorphism. Maybe I should have it like this. Well, okay. An isomorphism P from L prime is called an extension of phi. Well, if I restrict it to k, I get the small phi. So if phi restricted to k as a map from, so if phi restricted to k, so as a map to its image is equal to small phi. So this means that this map phi has the property that every element of k will be sent to k prime, and for an element in k prime, in k, we just get small phi. Okay, so this is simple. And so we will mostly be concerned with the case where k is equal to k prime. But not only. Mostly interested in case that k is equal to k prime and phi is the identity. Okay. And maybe even L is equal to L prime. So in that case, you have a field extension, so you have a field extension L over k, and you want to ask yourself, what are the k automorphisms of L? So then the extensions of phi are the k automorphisms. Okay. No, by definition. Okay, so let's look at it. Okay, so we can, for simple algebraic extensions, we can completely describe. So if you what these extensions of the field isomorphisms are. So let's first have the following simple remark. So if phi from k to k prime is a field isomorphism, and I take L over k and L prime over k prime field extensions, so no, I didn't know that. So I assume I have this field isomorphism. Then we have we get a ring homomorphism which I may call phi lower star from kx to phi prime of x by just applying this field isomorphism to the coefficients. So sum I equals 0 to n ai x to the I. So where the ai, I, and k is just sent to, so this I call g, is sent to sum I equals 0 to n phi of ai x to the I, which I would call phi star of t. Okay, so it's clear from the definition, so this is k prime. So it's clear that this is a ring homomorphism and in fact a ring isomorphism. Because if I take the product of, apply it to the product of two polynomials, I get a product because phi is a homomorphism. And you just simplify the same for the sum. And it's also an isomorphism because obviously the inverse is the phi to the minus 1 lower star. Okay, we want to use that. So now we have the following. I call it theorem, although it's not very difficult. So we take let L, let phi and k to k prime in field isomorphism. L over k and L prime over k prime field extensions. So actually we are not so much interested, so anyway, let A in L be algebraic over K. And so when I take, I write down as minimum polynomial. And we take any zero of applying this operation to the minimum polynomial. Is zero of phi star, phi lower star of Fa. Okay. Then the claim is there is a unique extension of phi as a map from L from Ka to Ka prime, which sends A to A prime. Then there exists a unique phi from K of A to K of K prime A prime, which is an extension. So, well, we need, I should have said the extension of phi. Which is an extension. Well, maybe I write a proper unique extension phi from K of A to A of A prime of phi with phi of A is equal to A prime. Okay. So maybe this is a bit confusing with this L and L prime, but in some sense we just have assume we have a simple algebraic extension Ka over K, and we take the minimal polynomial of this thing and we apply this field homomorphism to it, then we find in and the 0 of this in some other field, then there's a unique extension of this map here. So the most interesting case, as I said, was the case when k is equal to k prime and small phi is equal to the identity. So if k is equal to k prime and phi is equal to the identity of k, this says the following. We can also call it maybe theorem or maybe corollary. So let L over K, or maybe let A over K be a simple algebraic extension with the minimal polynomial. At A, then for any 0, I actually need this was a bit careless. I still actually need, so I take it with minimum polynomial of A, but I actually need to say I need to do now a bit more careful. So I say still, I just wipe it out. Let me try again. So, so I take a field extension and A element in L with minimum polynomial of A. So then for any 0, A prime in L of Fa that exists the unique K isomorphism phi from Ka to Ka prime with phi of A is equal to A prime. Okay, you can also, if you want, specialize a little bit more. For instance, you could put, like I just did, L equal to Ka. Okay, so if I also say L equal to Ka, then it says for any 0 A prime in K of A, there exists the unique K automorphism of Ka, sending A to A prime. What? Yeah, that's a big phi. You're right. So we will see that this, despite in the moment it's kind of some crazy thing which looks a bit abstract and not particularly useful, but we will use it many times. And so one should, so maybe I will therefore also spell this out. Also the last case, so this was, in this case we had k is equal to k prime, and phi is the identity, but we can also have k of a is equal to k prime. So we also say, so it also follows for any 0 a prime in Ka there exists a unique K automorphisms phi from Ka. So phi of Ka is phi of A is equal to A prime. So this particular, here in particular you see, and we will see later, the Galois group of the field extension Ka over K just is described in terms of the roots of this minimal polynomial. We'll later make use of that. It has, for instance, precisely as many elements as the minimal polynomial has roots in this field extension. So now we need to prove it. So we only need to prove the first statement, obviously, if you know with L, L prime, and so on. All the other ones are special cases. And this was a special case where K is equal to K prime and phi is the identity. And this was the special case where, in addition, L is equal to K. So first, I wiped out the statement, but we said there is a unique extension and so on. As usual, if you have existence and uniqueness, you prove the uniqueness first, because that tells you what the thing is. And then, so that by the condition, the thing is uniquely determined. And then you have to see that the thing which has been determined actually satisfies what you wanted to do. That's always, almost always the way how existence and uniqueness is shown. So, so we start with uniqueness. So we note that K of A can be written as a set of all G of A, where G is a polynomial with coefficients in X. Now remember that we had found that the finite extension is just Kx modulo the ideal generated by A, and the elements in this thing can be just viewed as all the polynomials G, where you put A as the argument. Obviously these are not all different for different polynomials, but this is how this can be described. We had seen this before. Remember? Okay, and so therefore also A prime of A prime is equal to all G prime of A with G prime and A prime. Okay. So now let's take any element G, which I can write some I equals 0 to n, say bi x to bi in Kx. So then a general element in Ka will be obtained by putting A into it. So now assume phi from Ka to K prime A prime is a homomorphism extending phi from K to K prime. Then if I take phi, so a general element here can be written as G of A. So phi of G of A I claim we can compute it by just what we have here. So, what is this? So, phi is supposed to be a homomorphism, so this is phi of sum I equals 0 to n, bi a to the I. And this phi is supposed to be a field homomorphism, so it means, it goes into the sum and it goes into the product, and its restriction to k is the small phi. So therefore, this is equal to sum I equals 0 to n phi of bi times large phi of ai. A first a to the I, but this also pulls out. So this is equal to sum I equals 0 to n phi of bi and a prime to the I. So if you want, you can write this according to what I wrote before. That's not very important. Anyway, this completely determines it. But if you want, you can also write this as phi star of g of a prime, according to how we have defined it. And you can see I have taken an arbitrary element from Ka and I have written down what its image is. So the map is uniquely determined. However, obviously, we have to see that this is well defined, or that this is a correct definition, because not all, for different g's, not necessarily the g of a's are different. No? So we have to see that this is the correct definition. So we prove the existence by showing that this prescription works. So existence. So we define phi from Ka to A prime. A prime by sending so if I write by sending that g of a, the g is any polynomial in Qx, is sent to phi prime phi star of g of a prime. So where a prime was okay. So remember, this was in the proof, but a prime is a zero of phi star of fa in F. No? Any zero. And this was minimal polynomial, and we apply this to it. So somehow we have to see it has something to do with this. So, obviously, if phi is well defined, it is a homomorphism. No, because we just the sum goes to the sum, the product to the product, but you have to make sure it's well defined. And okay, let me first go. Let me first see. Assume Okay, so what do I want to say? So, what I have to show. So first, assume. So, what do you want? So we have to show maybe that this map is well defined and injective. Maybe I first show it's well defined. So, if, what does it mean? So, if I have two different polynomials which give the same g of a, then we should get the same result. So, if g of a is equal to g prime of a, well, not g prime of a, h of a, then it follows this is equivalent to g minus h of a is equal to 0. And so we want to show, and then we have to show that phi star of g minus h of a is equal to 0. So thus we can assume, so basically therefore it's enough to see that if g of a is equal to 0, then phi star, so thus to see if g of a is equal to 0, then phi star g is equal to 0. Okay. So what does we assume? G of a is equal to 0. Then we know that then g lies, so the ideal of all polynomials in Kx which vanish at a is generated by the minimum polynomials. So then we can write g equal to fa times L with L in Kx, and thus it also follows that so if I take phi star of g, this is equal to phi star of fa times phi star of L, and thus g and thus what do I want to say? So if I apply this to a, g applied to a is equal to a prime this is equal to phi star of fa of a prime times phi star of L of a prime, and this by definition is phi of a, and you can see this is equal. So this one is 0, because we had assumed that a prime is 0 of this minimum polynomial, of the transform of minimum polynomial. So therefore the map is well defined, And basically, we can also see that it is injective. So if so that's well defined. So, on the other hand, if there's an element h of a which is in the kernel of p, and I think I could have made everything only if, but now I do it like this, then it follows that p star of h of a prime is equal to 0 by definition of this p. So by definition, if I take p star of fa, this is monic. Because fa is a polynomial which starts with 1, and if I have a field isomorphism, it sends 1 to 1. And so it's also monic and irreducible. Because fa was irreducible, and if I have an isomorphism, it sends irreducibles to irreducibles. So, thus it follows p star of fa is a monic irreducible polynomial with coefficients in k prime, which vanishes at a prime. So it is the minimal polynomial of a prime over k prime.
It means that even here we should divide by the leading coefficient of L first of all.
What?
Here, when we assume g of 0 equal to 0, and
why?
We just proved that phi star of g equals okay.
No, I think it's okay as it is. So anyway, so this is the minimum polynomial. And so thus, if I assume that h of a is in the kernel of phi, it means that this is equal to 0. So thus, it follows that this is divisible by, so we have phi star of fa divides phi star of h. No?
Sir, because here we have just evaluated phi star of j at a, at the a prime, and we have concluded that phi star of j is equal to 0.
No, we forgot a prime. We forgot a prime.
Where is the a prime?
The third line from the bottom.
Yeah. That's what I want to explain. That's what it means that it's well defined. No? We have a homomorphism. We want to see that if g of a is equal to 0, then phi of g of phi star of g of a, so which is this is phi of a is also equal to 0. But I forgot to write the a prime.
Phi of g of a.
Yeah, okay. Yeah, I make a bit more distance than usual. Okay, so so thus this divides this, So, and therefore, no, this is phi is a so this divides it in k prime of x. So thus fa divides h in kx, because this phi star is a ring isomorphism. So thus h of a is equal to 0. No, because f of a is equal to 0, so we can write h as fa times some other polynomial. So if I apply a, I get 0. So thus phi is injected. And by definition, again, phi is surjective, because the definition was just that any polynomial in g of a is sent to the corresponding polynomial in. Anyway, I just say by definition phi is surjective. Because the map was I have here a set of all g of a, g in kx. I send it with phi to the set of all phi star. So this was a set of all g prime, a prime, with g prime, and the x prime. By sending g of a to phi star g of a prime, and obviously phi star was an isomorphism, so every polynomial g, so every phi star of g we get here from all the g's, and so thus this means this map here is obviously surjective, because all this field is just all these polynomials applied to a prime, and these are all polynomials because we start with all polynomials. Okay, so this is this proof. I'm really going to do it really fast this way. Okay. Yeah, actually. So I just use up my. I hope it's okay. I used the full 1.5 hours after. I don't know if you have any appointment. Okay. And so finally, we also had the statement that phi should say a to the prime. No? By definition, if I have phi of a, this is equal to applying, so to speak, phi to the polynomial x applied at a. And so this is equal to phi star of x of a prime. But obviously, under this thing, you just map the coefficients. The coefficient is 1, the coefficient stays 1. So this is just x of a prime. So this is a prime. So we see that phi maps a to a prime. Okay, so this was this little thing. Okay, we will later go back to it. You should mostly maybe remember the last statement, that if we have a simple algebra extension where the minimum polynomial is fa, then for every other root of the minimal polynomial, or for every root of the minimal polynomial, there's a unique k automorphism of this extended field, which sends our given A to A prime, to the other root. Okay, now we let me see what time. Okay, I want to some kind of intermezzo. I can very briefly talk about algebraic closure, just so that we have this. I'm not really going to use it, but just as this is a standard concept that one sees often, I just want to introduce it, the algebraic closure of a field without proper proofs. So introduce the algebraic closure of a field without proofs. So this is following definition. So let A be a field, L is algebraically closed, if the following statements holds, if the following equivalent statement holds, so every polynomial with coefficients in L has a zero in L. Okay. And the second statement is, let's say every monic polynomial splits into linear factors. So every monic f in Lx splits as f is equal to x minus the 1 times x minus the n, where the ai are all elements in A. Okay. So these two statements are obviously equivalent. So the second statement is stronger. A general polynomial is just some constant, we just it has the leading term doesn't need to be 1, but it will be something, and so we just have c. It will therefore split as this constant times this, and so in particular it has zeros. And conversely, if we have a polynomial which has a 0, then we divide. So first we can make this polynomial monic. So if a polynomial is monic, it starts with 1, and if it has a 0, we can divide by x minus the 0. Then we have a polynomial of degree 1 less, and again we apply it to it, and inductively it splits into linear factor. So 2 to 1 is kind of trivial, and 1 to 2, so f will have a 0, a and L, so can write f equal to x minus a times g is g in Lx, and the degree of g is equal to the degree of f minus 1. Now, induction over the degree of f. Okay?
Is it every non-constant polynomial as is 0 for the first statement?
Yeah. Sorry. So, certainly that's correct. There was every non-constant polynomial. Obviously, otherwise it would be false. Lx is 0 in L. Yeah, okay. So I only make these mistakes to keep you paying attention. But anyway. Okay, so let's see. Clearly, Q and R are not algebraically closed. You can, for instance, if you take, for instance, square root of 2 is not an element in Q, but obviously is a solution 0 of x squared minus 2, and in the same way I is not an element in R, but we have that it's 0 of x squared plus 1. And these obviously are polynomials with coefficients in R or in Q. We have already seen by definition, so I have actually just told you before that Q bar is algebraically closed. So Q bar was a set of all elements in the complex numbers which are algebraic over Q. And I had explained to you that if an element is algebraic over Q bar, it already is algebraic. And so therefore it will be this Q bar is algebraically closed. So every element. Anyway. So what is the algebraic closure? It's somehow the smallest algebraic extension, which is algebraically closed. So definition field extension L over K is called an algebraic closure if L is algebraically closed and the extension L over K is algebraic. So every element in L satisfies an algebraic equation, but every element in L which satisfies a polynomial equation is already in L. Every element which satisfies a polynomial equation with coefficients in L already lies in L. So, and so the theorem is that this always exists. Every field has an algebraic closure. No. And so this is not, it's a bit, so one can prove this using the lemma of Zorn, similar, proving that every vector space has a basis. It's not particularly difficult if one likes such set theoretic stuff. Anyway, it's not difficult, but we're not going to use it. And so we have just seen, therefore, I should also maybe have said this before. Obviously, I'm using here that C is algebraically closed. So the fact that the complex numbers are algebraically closed is obviously not a statement of algebra, but a statement of analysis, because the complex numbers are an object of analysis. And we have this infinite construction. And this, I don't know how far you are in your complex analysis course, but certainly you are going to prove this in your complex analysis course. So this follows from complex.
The fundamental theorem of algebra?
Yeah, that's the fundamental theorem of algebra. And so therefore, from this, if C is algebraically closed, so then from this it follows that Q is algebraically closed.
There is no way to prove this with algebraic method.
No, I mean, well, I don't know, maybe, in some sense, well, I mean, I wouldn't say that. There might be some terribly complicated proof using algebra, but in some sense, the complex numbers itself are this infinite construction, so you wouldn't really want to work with it this way. I mean, they're defined like this, and so it's somehow not a statement of algebra. And so this follows from, this is the fundamental theorem of algebra. It follows from so-called Liouville's theorem, which you are going to see. So, and then we can see that that Q bar is the algebraic closure of Q. Because this we had just seen that Q is Q bar is algebraic over Q, and I had claimed it's algebraically closed. So, but I should maybe have said that the fact that, that Q bar is algebraically closed follows from the fact that C is algebraically closed. Because I take all elements in C which are algebraic, and then we know that this will be algebraically closed. And obviously C is not the algebraic closure of Q, because C is much too big. Most elements are not algebraic. C is the algebraic closure of R. Okay, so maybe I will stop here.